In this lecture, I'll cover inelastic column. So far, we studied assuming the column is always elastic range. Let's say Euler buckling load, that is the elastic range. I'll present the inelastic column. As you see, this is stress strain the relationship. When we do steel coupon tensile test, sigma stress equal P over A area, strain epsilon equal delta L over original length L. That is stress strain relationship of the steel, right? It is just the steel coupon. But if you consider this kind of column, very short column, okay, apply the load P. Then we can also calculate sigma, okay, P over whole area of this column, H column. The epsilon equal delta L over L. We apply some axial force, compressive force. But if we apply the tensile force, we have the same result. So then we can draw stress-strain relationship like this. Then the curve go up to here, and then it is not anymore the straight line. It curved like that. Why? It is due to residual stress. When you do the coupon test, there is no residual stresses. But when we make this column, we have residual stresses at this section. This tip part has compressive residual stress. This middle part and web has tensile residual stresses. Why? Because the cooling speed, each part is different. This tip part cool first. Later, this middle part cool. So this tip part has some compressive or residual stresses due to the different cooling speed. So how big of these residual stresses is the biggest one is about 30% of sigma y. If we see the stress state of this flange like this, but stress increase, then somewhere here we can draw like the stress diagram. It is convenient you think from this. Add the stress here, then stress diagram like that. So this part is yielding. This center part is elastic range. This part, the both side has the yielding stress. So after some part has yielding, there is no resistance, okay, regarding the additional force. So we call it the inelastic range. Okay, so stiffness degrade like that. This point, the whole section is yielding. So the section has no any resistance against additional loading. So curve like that. So let's look at this. If the long column just sustain a very small loading, so the stress also small. In case of long column, when the stress is, let's say, this sigma CR, the column buckle. But if we consider the short column, this column can sustain more loading, somewhat large loading. So the stress of this short column is somewhat bigger than long column case. So the short column buckle somewhere here. As you see here, the part of the section is already yielding, like this, already yielding. Elastic modulus cannot apply for the short column because up to sigma p, p means proportional. Stress strain relationship is proportional. The proportional range up to here, the elastic modulus E, this E works, but after sigma p, this modulus is not anymore elastic modulus. So we have to consider the change of this elastic modulus. So if this elastic long column case, PCR equal pi square EI over L square. So if you divide by A, you can get sigma CR, okay? Divided by A like that. if you move this I to downside, then you can get R, right? R equal square root 2 I of A, right? This equation can be written as this. This is some stress at buckling. We call it buckling stress. So if this buckling stress less than sigma p proportional the limit, then we call it elastic buckling. Elastic buckling occur in long column, so we call it Euler buckling load. If sigma CL is greater than sigma P, this range, it is not Euler buckling case anymore. So we call it inelastic buckling in case of a short column. We can draw some buckling stress, column strength in terms of stress. If the long column, Euler buckling load is valid, okay? So elastic buckling, okay? If a short column, the part of section is already yielded, so Euler buckling load cannot apply. Euler buckling stress cannot apply. So we have to consider inelastic column behavior. So let's look at that column behavior. Yeah, this is simply supported column. If we draw stress-strain relationship, then up to here is the slope is E. Okay. After this proportional limit, it shows some curve. In this range, we call E, the slope is called EFF, effective E. That means the inelastic column. So far you learned this kind of pre-bi diagram. M internal equal minus EI Y2 prime. This E is this elastic column E. If a short column case, let's assume this is short column, then take out this part, pre-bi diagram, PP, M internal moment. M internal moment is minus E effective I Y2 prime. This slope, not here. So this is inelastic column. Yeah, so elastic PCR is this one. Inelastic PCR is pi EFF, effective E. Yeah, this term is different. Elastic E, inelastic EFF. I'll introduce ET and ER as EFF. There are two different EFF. One is ET, one is ER. ET is called tangent modular theory. ER is reduced modular theory or double modular theory. So I'd like to present two different concepts. I'd like to introduce tangent modular theory. Firstly, simply support the column here. Take out the pre-bi diagram, PP, and internal moment. In tangent modular theory, we assume no strain reversal. So in this approach, we assume delta P and delta P applied at the same time. It means we consider the loading P1. P1 is just before the buckling load. PT is the buckling load, inelastic buckling load, tangent buckling load. P1 is just before this buckling load. In this tangent modular theory, firstly we consider E epsilon 1 at this point, just before the buckling load, epsilon 1 due to P1. Here, P increase, then sigma increase. Then we consider epsilon 1, somewhere in epsilon 1, just before the buckling. And then we assume delta P and delta M applied at the same time. That means due to delta P, we have this uniform delta epsilon P, okay, the strain. Due to delta M, we have this compressive stress and right hand side. Here, left hand side, we have the tensile strain. Why? This one is epsilon 1, and then we have to add together this one, delta epsilon. This one is plus delta epsilon P. This one is minus delta epsilon M. We consider this magnitude is identical. We assume like that. So this is 0, okay? This one plus minus 0. So when the buckle occur, the strain status like this. As you see, from epsilon 1, the strain always increase, this increase, at least greater than 0 or equal to 0, this strain. So strain increase this right hand side, so the stress can be calculated following this slope called epsilon t, tangent modulus. This is tangent line, right? So tangent modulus. So m internal equal minus et I y2 prime here. So we can rewrite equation like this, and then ei y2 prime. If we let k square equal p eti, then we can solve the same as the previous. Pt equal pi square eti over L square. Okay, it is called tangent modulus load for inelastic column. We can rewrite as a function of Euler buckling load et over ep, right? Yeah. If you look at this curve again, sigma delta equal delta epsilon the slope et. This is tangent modulus theory. So another theory is double modulus theory, okay, for inelastic column. It is a little complicated compared to tangent modulus theory. I'd like to drive double modulus. Okay, let's look at this. This is a column. Assume the column buckle in this way, right hand side. Left hand side and right hand side, it doesn't matter. But the better presentation, I assume left hand side buckle. Then that is a free body diagram and internal moment like this. Here, this double modular theory, we assume strain reversal occur. That means the loading get to this PR, buckling load, inelastic buckling load, and then this bending occur. That is the assumption. The buckling load increase up to PR, and then it buckle. If you look at this curve, the P increase up to PR, that means the sigma increase up to sigma R, this point. And then it buckle. Buckle means bending moment apply, like that. Bending, buckling, or bending or buckling occur after P reach PR. That is the assumption. Then let's look at the strain curve first. Firstly, this point is epsilon 1, okay, corresponding to buckling stress. Okay, that is epsilon 1. And then what happened? Small bending occur, buckling occur. So stress due to bending occur. So strain occur. As you see, moment occur the clockwise. This is compressive E1. This right hand side is compressive. Delta epsilon 1. So strain increase here. From this is epsilon 1 and then delta epsilon 1. As you see, delta epsilon 1. And then this left hand side, what happened? Due to bending, this bending stress, this one strain decrease, okay? Because left hand side is tensile stress occur when it is subjected to this bending moment. So epsilon 1 is compressive stress. This tensile stress occur. How much? Delta epsilon 2 due to this tensile side, due to bending. That is delta epsilon 2. You know, this angle is curvature. So delta epsilon 1 equal this C1. This is C1. This is C1 times curvature because small deflection theory. This is C1 times curvature is this one. Okay, delta epsilon 1. This delta epsilon 2 equal this is C2. C2 times curvature. Delta epsilon 2 due to small deformation theory. Okay, this is a bifurcation approach. So it is still small displacement theory. So this equation satisfies. Now let's calculate stress. As you see, the strain always keep the plane, the straight line. That is strain. But stress is different. How to calculate this stress? This is stress diagram. From here, that is right hand side, compressive side. The strain increase like that, delta epsilon 1. And then this slope is epsilon t. So this change of that stress is a delta sigma 1. So delta sigma 1 equal what? Delta epsilon 1 times et. So delta sigma 1 equal ET times this delta epsilon 1. This delta epsilon 1 equals C1 curvature. So like that. How about the delta sigma 2? The strain reduced delta epsilon 2. So how to calculate the equivalent delta sigma 2? Then delta epsilon 2 times E. Delta epsilon 2 times E. YE. When the strain reverse, the slope is equal to original Young modulus, elastic modulus. That is the characteristic of the sphere. The slope when the strain decrease is E. So we can calculate delta sigma 2 equal delta epsilon 2 times E. So delta sigma 2 equal E times delta epsilon 2. Delta epsilon 2 equal C2 curvature. That is the relationship. So we call this modulus is double modulus theory. Why double? Right hand side governs ET. Left hand side is E. There are two different modulus, E and ET. So we call it double modulus theory. Another term is that reduced modular theory. Why reduced? The strain reduced. So we call it reduced modular theory. It has two different names. So PR equal pi square ERI S square. Okay. This ER double modulus. This is double modulus load, buckling load for inelastic column. Now we have to calculate ER. We know E, we know ET. They are related here. They are involved here. So we have to calculate ER. It is a function of ET and E. Let's calculate for rectangular section because the rectangular section is the easiest one. We have to understand the concept. So we use the easiest case, the rectangular section. Firstly, we consider force equilibrium. As you see, delta PT must be equal to delta PC. So delta PT can be calculated by this the area of this triangle. So 1 over 2, this height is E C2 pi, this length is C2. B equal width of this section. Right hand side also 1 over 2. This height is ETC1 pi. C1 and then width B. From this equation we can get this equation number 1. EC2 square ETC1 square because these can be deleted. And then we also consider the geometry. C1 plus C2 equal H. Finally we get equation 1 and 2. Using this equation, we can get ER for rectangular section. From equation 1 and 2, unknown is C1 and C2. Okay, we know H, we know E, we know ET. Tangent modulus we know graphically. So we have to get the C1 and C2. We have two equations. We can get C1 and C2 like this equation from equation 1 and 2. Okay. And then M internal moment equal P compressive load times C or P tensile load times C. This P and distance C. If this is H, this C is 2 over 3H, right? So P compressive is 1 over 2 ET C1 pi. Yeah, this one. And C1B. Okay, yeah, this one, right? That is delta PC. And times C. It is delta PT and delta PC is coupled load, coupled force times this moment arm. We calculate like that. And the C1 square is this one. Okay, the square and 1 over 2 ET pi B C equal 2 over 3H. Okay, moment arm. Then we can rewrite like this. And then we can rewrite like this equation. 1 over 12 BH cube is, what is this? That is I, right? Moment of inertia of rectangular section. That is curvature. So moment equal I E curvature. It is called ER, reduced modulus or double modulus. Same term, ER. This is ER. M moment equal I modulus and curvature. So this is ER. So ER is this one. So this PR equal pi square ER I over S square. So we can rewrite ER over E PE. So ER is this equation for rectangular section. If we consider some H section, yeah, it might be more complicated when you consider both flange and web. For rectangular section, we can draw the curve. This sigma L over R. We can draw the curve. Then that is sigma T, sigma R up to here. Sigma R and sigma T equal 4 inelastic column, right? From here, long column, overlapping stress. So if we draw for rectangular column, sigma R curve like this, upper bound. Sigma T is somewhere low, like this. When you test the column, that is test result X. That is somewhere between sigma T and sigma R, but it is closer to sigma T, tangent modular theory stress.